Welcome back to Tales of Chemistry. In this episode, we are actually discussing valence bond theory, which is written in short form VBT, valence bond theory. So, in this valence bond theory, what we are looking forward is a technique to know the geometry or the shape, color, magnetic character, etc. of a compound. I repeat, geometry of a compound, the color of the compound, magnetic character of the compound. All these are explained by valence bond theory. Now, let me take an example and along with the example, explain the postulates of valence bond theory. So the first example that I'm going to take is FeCN 6 times, and the charge on the complex is 3 minus. In this, central metal is Fe. The electronic configuration of Fe is atomic number is 26, so electronic configuration 3d6 4s2. This you please learn as it is. 3d6 4s2. Now, we need to find the charge on the metal. So let me take it as X and Cn6 minus 6. So X minus 6 is equal to minus 3. So X is minus 3 plus 6, which is plus 3. So here Fe is in the plus 3 oxidation state. Then what will be the electronic configuration of Fe3 plus? You need to remove 3 electrons. I'm removing 2 from 4s2 and 1 electron from 3d6. So at present, the electronic configuration is 3d5. So Fe was 3d6, 3d 5 orbitals, right? 1, 2, 3, 4, 5, 6 and 4s with 2 electrons. Now, in Fe3 plus, the electronic configuration is 3d5. So 1, 2, 3, 4, 5 and 4s has no electron. Now, when the ligands approach, when the ligands approach, how many empty orbitals are needed? 6 ligands are there. So, 6 empty orbitals are needed. But do you have 6 empty orbitals? No, you don't. You just have the 4s orbital empty. So, you will have to bring in the 4p orbitals. Also, one more point that we are noticing here is, I'll write it here, the ligand. What is the ligand? Cn minus. Okay, so Cn minus, cyanide is a strong field ligand. Okay, I've written strong ligand. It is a strong field ligand. What does that mean? This means that the d orbital electron, the 3d electrons are forced to pair up. Forced to pair up. Who's forcing them to pair up? The strong ligand, which means now the present 3d will be, totally 5 electrons, and you are forcing them to pair up 2, 4 and 5. Now you need 6 orbitals empty. Let us see whether we have 6 orbitals empty. So I have 2 orbitals in 3d, 1 in 4s. These are the 2 from 3d, 4s and 4 electrons, 4 orbitals in 4p. So what are the orbitals that are undergoing combination? 2 of the d orbitals. So I write d2, s and 3p orbital. The hybridization that is taking place here is D2sp3 hybridization. What is hybridization actually? Intermixing of atomic orbitals of identical energy to form equal number of hybridized orbitals. 1, 2, 3, 4, 5, and 6. So 6 orbitals are combining and you will get 6 hybridized orbital. Each of these orbital will receive a pair of electron from the cyanides. 6 cyanides are there and 6 orbitals are there. So each of the orbital will receive a pair of electron. So point number 1 that you are noticing here, what is hybridization? Your answer is D2sp3, and this hybridization will decide the geometry of the molecule. D2sp3 will lead to a octahedral shape or octahedral geometry. Another point is the magnetic character. You're seeing one electron here that is unpaired. So if you see at least one unpaired electron, then such a complex is paramagnetic in nature. It is paramagnetic due to the presence of unpaired electron. Paramagnetic due to the presence of unpaired electron in 3D. What else? Is this an inner orbital or an outer orbital complex? Okay. So this is a inner orbital complex. Inner orbital complex. Why is this an inner orbital complex? Okay. 3D orbitals are used. 3D orbitals are used for hybridization. I mean to say, the d orbitals that are used are coming before the s and the p orbital. The d orbitals are present or positioned before the s and p. 3d, 4s and 4p. Okay, so because the d orbitals are appearing before the 4s and 4p, these are called inner orbital complexes. All right, hybridization, geometry, magnetic character, as well as the inner orbital or outer orbital. These are the questions. Now, how are they asking this question? They'll give you the complex FeCN6 3 minus. Okay. What is the hybridization? Predict the hybridization, geometry, magnetic character of this example. Is this an inner orbital complex or outer orbital complex? So each answer is worth half a mark only. Okay, so moving on with another example, one more example. CO NH3 6 times, charge is 3 plus. So here the central metal is cobalt. Cobalt has a configuration of 3d7 and 4s2. Next is to find out the charge. X plus 0 is equal to plus 3. So X is also plus 3. CO3 plus is 3D 6 and 4 is 0. Now here I'll straight away write CO3 plus itself, 3D orbitals and the 4s. I may require 4p. Now 3D the 4s orbital and the 4p orbitals. Okay, so in this 3D, you have 6 electrons, right? 1, 2, 3, 4, 5, 6. 4s is 0, 4p is kept. If needed, we will use it. Now, how many ligands are there? 6 ligands are there. And you need 6 empty orbitals. Even if you take the 4p now, you have only 4 orbitals, but you need 6 of them. Again, NH3, just like I told you in the case, NH3 is a strong field ligand, just like, I told you in the case of cyanide. This is also a strong field ligand, which means NH3 will force the 3D electrons to pair up. Now, what will be the condition CO3 plus when the ligands approach? When the ligands approach, there is force pairing. So, the 3D orbital now will be like this. 6 electrons are paired up. Your 4s is empty. 4p also is empty. Now, the 6 orbitals that undergo hybridization are these 6 orbitals. How do I name them? D2, because the first 2 are d orbital, s and p, 3 of the p orbitals. So here again, the hybridization is D2sp3 hybridization. D2sp3 will lead to octahedral geometry. Now, let me draw the hybridized orbitals. All the 6 of them, I'm putting them together. Okay, now each one of these will receive a pair of a pair of electron from the ligand. There are 6 ligands, so 6 pairs of electrons are received by the hybridized orbital. Since D comes before S and P, this is inner orbital complex. Geometry is octahedral, and magnetic character, this is diamagnetic. Why is this diamagnetic? That is because you don't have any unpaired electrons. No unpaired electrons are present. So this particular example is an example for a diamagnetic complex. The next example that we are discussing, COF6 3 minus, COF6 3 minus. Once again, this is cobalt. 27 is atomic number. 3d7, 4s2 is the configuration. Charge x minus 6 is minus 3. X is equal to plus 3. So CO3 plus, which is 3d6. So straight away, let me write CO3 plus, okay, that is the 3D orbitals. 6 electrons are there. So 2, 3, 4, 5, 6. 4s is now empty. I'm keeping the 4p ready. If I need, I will use it. Okay, then coming to the point here, F minus or the fluoride is a weak field ligand. It is a weak ligand or a weak field ligand. So, no force pairing takes place. No force pairing, which means I have a little bit of a difficulty here to, collect the required number of orbitals. There are 6 ligands, right? 6 ligands, but the ligands are weak. So they cannot force the d electrons to pair up. Now, I have no choice but bring in the 4d orbitals also. I don't require all of them, but I may need 1 or 2 of the 4d. Let's see how many do I need. There are 6 fluorides. So 1, 2, 3, 4, 5, 6. I need 6 of these. Okay, these are the orbitals that undergo hybridization. These are the orbitals that undergo hybridization. How do I name that hybridized orbital? P3, because 3 of the p orbitals are taken, and D2, sp3 D2 is hybridization. Now, where is the position of the d orbital? The d orbital is present after the s and the p. Okay, so here this is an outer orbital complex. This is a outer orbital complex because the d is positioned after s and p. Now, magnetic character, this will be highly paramagnetic. Why is it highly paramagnetic? Because you have a lot of unpaired electrons. Okay, so instead of highly paramagnetic, this can also be called a high spin complex. Yeah, so many unpaired electrons are there that makes the complex a high spin complex. Okay. Now, generally, the outer orbital complexes are examples for high spin complexes. Generally, I said not always though. Then, that is all about COF6. Its geometry is again octahedral. Okay, because of sp3d2 configuration. So pointers d2sp3 as well as sp3d2 leads to octahedral complexes. Now sp3d2 is outer orbital. This is a highly paramagnetic complex. Okay, now the next example, which probably you can work out when you get time, is FeH2O6 3 plus. Okay, charge on Fe is 3 plus. Okay, so these are the clue that I'm giving you. And regarding the strength of the ligand, aqua is a weak field ligand. This is also a high spin or highly paramagnetic complex. Highly paramagnetic complex, and the sp3d2 hybridization is sp3d2 hybridization sp3d2. Okay, so that is all regarding D2sp3 and sp3d2, that is octahedral complexes. Stay tuned for more videos and thank you for watching.